I always love talking to people about cryptography. I'm passionate about trying to teach cryptography, and the Coursera course was a great example of this. As I was watching Laurie's talk, though, I was struck by the fact that it's very easy to distinguish a talk by an HCI expert from a talk by a cryptographer, because basically everywhere where she had pictures of people, I think I just put random math symbols. And, but actually, there's not very much math in this talk. But the truth is that her talk was actually a great background for what I'm going to be talking about today, because my talk today is not, I think, so much about the cryptography. It's actually also about users. It's actually also going to be about developers, so following up on the last question, actually. And thinking about maybe ways that we can change the way things are done, both from a usability standpoint as well as perhaps from a training standpoint, to try to reduce the prevalence of crypto flaws. But just by way of setting some background and setting the stage for what I'm going to talk about, I'll start off by giving some good news and some bad news. And of course, I'll start off with the bad news first. And the bad news, of course, and the reason why I'm giving this talk, is the fact that crypto is hard. And this leads to many flaws. And just to be clear, right, I don't mean, actually, for the purposes of this talk, that the underlying mathematics is difficult, although it is. But what I'm referring to specifically here is the fact that implementing crypto is hard. And I would claim, actually, that implementing crypto is currently hard, but this is not inherent, and it doesn't have to be that way. And what I'm proposing toward the end of the talk, I guess, is, again, some ideas that maybe we can use to try to improve the way things are done and improve the current state of practice. Now, the good news, actually, of the fact that crypto is hard is that it's so hard, in fact, to get right that even the bad guys get it wrong. And I saw this article actually just last week. It's not new, though, but the idea that attackers that are writing ransomware, right, are now getting the crypto wrong themselves. So when they install ransomware on your computer and they encrypt the contents of your hard drive, it turns out that in many instances, actually, researchers were able to reverse engineer the code, look at what's going on, and say, hey, the attacker was using bad randomness for generating the key, or they were using a public key algorithm rather than a symmetric key algorithm, or vice versa, I guess. And they were able, therefore, to actually recover the data from the infected users without paying the ransom. So this is great, right? So it's, maybe we should make crypto harder, and then even the people writing ransomware will get it wrong. And I hope, actually, I guess I should say that there's no one in the audience who's writing ransomware, and will learn something from this talk. But I don't think, of course, that this is the way to proceed. I don't think that we can hope to rely on hard crypto, on the fact that crypto is hard to implement for security. And in fact, we see quite often the opposite in practice. And if you look, actually, at crypto flaws, so there's certainly tons of crypto flaws constantly being reported. But in fact, there are many examples, and this is a historical list. It goes back maybe 15, 20 years, actually. But if you look, actually, there are many real-world instances of crypto flaws not only leading to exploitable bugs, but leading, actually, to real-world exploits. I think many of these are quite famous. WEP, the insecurity of WEP, and the fact that you can now that you can download, actually, for several years now, tools that will let you easily crack WEP. Other instances maybe got less notice in the general community, but were sort of widely discussed among cryptographers. And so these are real issues. These lead to real flaws and can lead to real attacks as well. Just to be clear about the scope of the talk and what I mean when I talk about a crypto flaw. So what I'm particularly interested in here is developer misuse of crypto and crypto libraries. So looking at the programmer, looking at how they're using crypto in their applications, how they're using crypto libraries when writing their code. And very often, especially nowadays, because this is sort of old hat, right? All these basic crypto bugs, and I'll talk about some of them in the course of the talk. But these are all kind of old hat, and they don't get as much press anymore, at least among the general public. And what does tend to get a lot of press are the more sexy kind of things. And these are out of the scope for the talk. These are kind of things that we'll get to once we fix the problems in the first bullet. So things that I'm not interested in today for the purposes of this talk are things like the possibility of crypto backdoors in software, the possibilities of low-level vulnerabilities in crypto libraries. So I'm again focusing on people who are using these crypto libraries to build applications that use cryptography. I'm not focusing on bugs in the crypto libraries themselves, things like timing attacks or buffer overflows or other kind of errors like that. I mean, those are important too, but that's, again, not what I'm looking at here. And I'm also not interested in the latest and greatest acronym, right? These attacks on complex protocols like TLS, like the Beast attack, the Crime attack, and all that. I mean, those are great. Those are interesting. Those are fun for me because they're really they're great research results. I don't think they actually have tended to lead to important real-world exploits. Maybe I'm wrong, but I think they're more proofs of concept, and we should be fixing those. But they haven't actually led to real attacks. And again, what this shows is how complicated just getting the underlying mathematical crypto and the underlying protocols correct is. But again, I'm not focusing on that today. What I want to focus on is just the standard plain vanilla crypto that we all learn in Crypto 101 and how developers use or misuse that basic crypto. And as examples, we can look at some very simple rules that I'm guessing many of you in the audience know or have seen before, whether you're working with crypto yourselves or whether you've taken a crypto class before. These are actually taken from a paper that I'll talk about later that was looking at prevalence of crypto flaws in software. And what they did was they just set a very low bar, I guess what I would call a very low bar. They looked for 6 very basic yet very common flaws in crypto code. For example, things like using deterministic encryption. Using deterministic encryption is, actually maybe I should ask, how many people in this room have taken a Crypto 101 class? Oh, so very many people. Okay, so I'll go a little faster through some of this. So using deterministic encryption is bad, and it should be avoided, ECB mode in particular. Using a quote-unquote randomized encryption scheme, but with a non-random IV is also bad. So hard coding, for example, an IV when using CBC mode, or using a low entropy IV in CBC mode is bad. Of course, using low entropy encryption keys is going to kill you right away. If the attacker can guess the key, you're going to have no security. Using non-salted hashes when you're hashing passwords is again a very common thing that's not only very basic and very important, but has actually again led to many practical examples of password database compromises, followed by the ability to recover users' passwords from those databases, which would have been less possible or less easy if those passwords had been salted. And again, another example of using low entropy is things like seeding a pseudorandom number generator with fixed constants or low entropy seeds. So these are the kind of basic crypto flaws that I'm interested in focusing on here and how we can prevent these from continuing to occur. And what's particularly frustrating about this is that none of this is new. And you can look back 20, 25 years ago at some papers that were published in the academic literature. A famous one is perhaps Ross Anderson, and actually I'm not aware, I was looking for an earlier reference. If anybody knows of an earlier reference talking about crypto flaws in deployed software, I'd be interested to hear about it. But the earliest one I know is by Ross Anderson in 1993. Okay, 25 years ago. This is like prehistory. This is, people were still using DES. And people were not using elliptic curve cryptography. And yet, the same flaws that he was talking about in his article are the same flaws we continue to see today. There's an essay by Bruce Schneier in 1998. Work by Gutman looking at lessons learned in implementing and deploying crypto software. So again, these are not new issues. These are old issues that people have been talking about for a long time. And nevertheless, we see that these issues remain. So for those of you who aren't aware, the IEEE Cybersecurity Committee has published a list of top 10 security design flaws in an attempt to try to educate the public, or educate the developer community, I suppose, on common flaws to avoid. And if you look at these 10, well, so first of all, one of them is using cryptography correctly. So this gets a whole a bullet as one of the top 10 security flaws. But in fact, if you read the article, you'll see that very many of the other top 10 security design flaws mention crypto explicitly, actually, in the discussion. And they clearly rely very much on crypto, among other things. But they fundamentally rely on crypto. And if the crypto is not done correctly, then some of these other design flaws will also occur in the system. And as I said, even though this is an old problem, the problem is still here. So Veracode came out with a white paper called The State of Software Security. This is from 2015. And what they did was they did an analysis of mobile apps. And they found that more than 80% of them had crypto flaws. I don't know if you'll be able to see this sufficiently, but yeah, you can see actually, right, so the most common flaw was insufficient entropy, but there are several others that are occurring with non-negligible probability, right, and this is in 2015. And in fact, what they found was that crypto problems in the software were in fact more common than other things that perhaps people might naturally think about as what might the most common flaws be, they're more common than things like cross-site scripting or SQL injection or actually anything else that they looked at in this study. Crypto problems were the ones that were occurring most often. In the academic literature, people have done several studies looking at, again, prevalence of crypto flaws in software. This paper from ACM CCS 2013 found something similar to the Veracode study, actually, that 88% of Android developers using crypto APIs were making mistakes. And again, for the most part, these were very basic mistakes, right? The problems that they were making were things like choosing weak keys, low entropy keys, setting poor parameters for their cryptography, using deprecated or weak algorithms, using insufficient entropy for other purposes, and ineffective password hashing, things that we mentioned before. 2014, there was another analysis of 269 crypto vulnerabilities in the CVE database from about 2011 to 2014. And what they found were that 83% of those crypto vulnerabilities were due to crypto misuse rather than the more complicated types of crypto attacks that I said were out of scope on my earlier slide. And again, the things that they found were, well, this should look familiar. This is 3 out of the 4 here are similar to what I had on the previous slide, right? They found weak keys, weak parameters, deprecated weak algorithms, and insufficient entropy. They also looked at just developers neglecting to encrypt sensitive data. And if you think about how we might avoid these crypto flaws, right? Well, it's easy to come up with a laundry list of design principles or guidelines that people should follow when writing their crypto code, right? So I can just turn around, I can negate the list on the previous slide, and I can say, well, you know, don't use weak keys and weak crypto parameters, and don't use deprecated and weak crypto algorithms, and make sure you're using sufficient entropy for your purposes. And you can go on, actually. So, right, so if you look, you'll find these in several places. Things like don't use a keyed hash as a message authentication code. Don't use textbook RSA signatures and encryption. Always use authenticated encryption. You know, avoid timing vulnerabilities, and et cetera. And maybe some of you might have expected that this would be the talk, that I would go through some of these and explain exactly what these principles are and why they're good ideas. But actually, I decided I don't want to do that. And the reason I don't want to do that is because you've probably all seen talks like that before, for one thing. And if you haven't seen a talk like that before, then you can find these by Googling. You can find on YouTube talks about, you know, how to avoid common crypto vulnerabilities by exactly following this laundry list of recommendations. Some of them explain the recommendations by going into the low-level details. Some of them don't explain them. But you can find this all over the place, and I didn't want to talk about that here. What I wanted to talk about instead was to look at some maybe common themes that underlie some of the most common crypto flaws that we see, and then explore whether we can learn something from those common themes to, again, improving the state of practice beyond just giving a laundry list of recommendations. And at least when I was looking at this, when I thought about it, what I noticed was that there seemed to be 2 common themes in these crypto flaws that keep occurring. The first of those, I would say, is unusable cryptography or unusable cryptographic libraries. And the second, I would say, is a misunderstanding of cryptography on the part of developers. In the first case, and I think both of these actually, I'm not laying the blame on developers here for either of them, maybe partially for the second bullet. I think actually for the first bullet, it's clearly the technical cryptographic community that has done, historically speaking, I guess I would have to say a poor job in developing the available crypto libraries for the most part. And I would say for the second bullet that maybe we need to rethink the way that we're educating people in cryptography and the way people are learning cryptography. So we'll see what you think about that. I would argue, though, that both of these have the same underlying cause, right? So the one issue was the unusable cryptography, unusable cryptographic libraries, and the second was an incorrect or not the right understanding of cryptography on the part of developers. And I think the cause in both cases really boils down to an incomplete or a fuzzy separation between the specification of what you want the crypto to achieve, and you could think about this as the API for your crypto, and the underlying implementation, the underlying mechanism, the underlying cryptographic scheme, the low-level cryptographic primitives. And if you think about it, right, imagine from the point of view of a developer that they want to build some messaging application, right, and they want to use, they know that they should be encrypting the content so that an eavesdropper can't read the traffic, and so they want to use public key encryption, okay? So how can you go about using public key encryption in your system? Well, if you go down to the details, right, the developer has to make a couple of choices. So if they're using public key encryption, if they want to do it efficiently, they're going to have to use hybrid encryption, which means they're going to have to couple a public key encapsulation scheme with some symmetric key encryption algorithm. For the key encapsulation component, they're going to have to make a decision about whether they want to use an RSA-based system or a discrete log-based system. They would have to know in the RSA case to use something like RSA OEEP. If they wanted to use a discrete log-based system, maybe they know enough to use DHIES, although I don't know how many people in the audience actually even know what that is. And then they have to determine in that case whether they want to use sort of classical Diffie-Hellman type discrete log system or an elliptic curve system. And on the symmetric key side, they have to decide, they have to make a choice, I should say, to use perhaps an authenticated encryption scheme. Perhaps they'll use an authenticated encryption scheme constructed in a generic fashion from an underlying secure encryption scheme, a CPA secure encryption scheme, and an underlying message authentication code. They would have to then know, okay, I better use CBC mode encryption for my underlying encryption, and I better use a secure version of CBC MAC for my message authentication code. And then they have to know further to go ahead and base those on a secure block cipher, maybe AES 128. Right? And this is kind of a mess, right? Because from the point of view of the developer, all they cared about was getting public key encryption. Why do they need to know? Why do they need to be exposed to all the underlying complexity in order to obtain the functionality of public key encryption? So let's look first at the question of usable cryptography, right? So typically, when people talk about usable security and usable cryptography, they think about the usability by the end users, right? And of course, there's this classic paper from 1999, Why Johnny Can't Encrypt. I recommend reading it. Actually, I read it for a talk I gave about 6 months ago. I took a look at it again, and it's very easy to read, very cute, very enjoyable. Of course, it's not so enjoyable when you realize that many of the problems are still around today. But anyway, people have classically looked at the usability of crypto by the end users. But what I'm interested in here is, right, usability of crypto and usability of crypto libraries by developers, right, by people who want to actually deploy this crypto and use it in their application. And there's been less work on this problem. Some more work recently. I'll touch on this in a few slides. But let me just show you a problem developers face. I already kind of touched on this in my previous slide, showing how complicated it can be to implement public key encryption. But let's look at this in a little bit more detail. So let me go quickly through this, because I didn't know how many people in the audience might have been familiar with private key encryption and message authentication. But I'll jump through this very quickly. So we have, two users share a key. You encrypt a message and generate a ciphertext. You send a ciphertext across the channel, and the other side, using the same key, can decrypt it to recover the message. And the security goal that we're interested in here, the security goal that's classically provided by an encryption scheme, is that an eavesdropping attacker should... You're pointing to me? Oh. Almost as exciting as the rain delay in last night's game. Anyway, so the eavesdropping attacker, right, who sees the ciphertext should learn nothing about the message. And in contrast, another symmetric key primitive called message authentication, you again have two users with a shared key. Now I've given a slightly different notation from what's standard here, but now one side will encode a message and generate some encoded message, which I call C, but it's not really a ciphertext, perhaps. And they send it to the other party. The other party can decode that to recover the message. And the security goal here is different, right? The security goal here is that an attacker who observes the encodings of several messages, M1, M2, M3, should then not be able to generate a new encoding C that can fool the receiver into outputting any new message M star that hasn't been explicitly sent by the sender before. So if the attacker then injects C star on this channel between the sender and receiver, basically the receiver should either output a previous message, like it's a replay attack, which can be handled using other means, or they should generate an error. Okay? And we know, of course, how to achieve both of these 20 years or so. CBC mode encryption is one way of achieving secure encryption. In CBC mode encryption, you have this iterative structure here where I've displayed the message as a sequence of blocks, M1, M2, M3. what you do is you pick a random IV, and then you chain things together in the way I've indicated here, and you output the ciphertext, which is a sequence of blocks C1, C2, C3. And again, I'm assuming that most of you have seen this already. CBC MAC works very similarly. It has the same iterated structure, but for CBC MAC, there's no random IV. Instead, if you want a secure version of CBC MAC that can handle variable length messages, what you do is you prepend the message length, and then you again compute this iterated chaining-like structure here, and then you take the final block of output, and the encoding of your message would actually be the message, comma, that last portion tag, the tag T. Okay? And if you want to implement CBC in OpenSSL, as an example, well, it turns out to be not too bad, I think, right? Because what OpenSSL provides for you is a CBC function that exactly implements this iterated structure. So what it does is it takes as input a key, an IV, and a message, and it computes exactly this function here. And if you want to do CBC mode encryption, what you do is you choose the IV at random, and essentially you're going to call CBC, the CBC function with your key, your IV, and your message, and then you return the IV plus the output of that function as your ciphertext. And if you want CBC MAC, what you do is you call the CBC algorithm with an all-zero IV. And then your input, your message, quote unquote, is now you prepend the length of the message, and then you put the message itself, and you call the function on that. You get the result, but then rather than using the result, you just take the last block size bytes of the result, where the block size here refers to the block size of the underlying block cipher. So clearly, nothing can go wrong here, right? I mean, there's no possibility of confusion. In fact, there's a lot of problems that can arise, because these algorithms, both of them are actually quite brittle. So I'll just walk through them very briefly. So CBC mode encryption, for example, is only secure when it's used with an unpredictable IV. If you call it with a zero IV, it's not going to be secure. If you call it with a nonce, which is predictable, it's also not secure. And, and furthermore, you may also even risk getting incorrect decryption, because if you just take the result of the CBC algorithm and forget about the IV, then the other side, in fact, will not be able to decrypt the entire message because they don't have the IV. CBC MAC is also known to be very brittle. If you return the entire result of the CBC function, rather than only the last block size number of bytes, it's insecure. And if you return rather too many or too few bytes from the end of the function, it's also insecure. Returning the last block but forgetting to prepend the message length is also insecure in general. And using a random IV in this case can actually also be insecure and or incorrect, depending on exactly how you implement things. Now, fortunately, oh, and I should mention, right, so you can also have bad interactions between CBC mode encryption and MAC, even if you did everything properly. Just as one example, if you use the same key for both, it'll be insecure. Now, fortunately, you can turn to the OpenSSL documentation, and it will help you figure out exactly how to implement these things properly. Because it had the following, I always enjoyed this quote. So normally, CBC is found as the function algorithm of CBC encrypt, but be aware that this is not really CBC. It does not update the IV. Use alg and CBC encrypt instead. I actually have no idea what that means, but I can only assume that as a developer, one would find that confusing. And then there's a statement in there that the use of different starting variables, which is what they also call the IV, prevents the same plain text enciphering to the same ciphertext. In that case, it's actually incorrect advice, right? So if you had, for example, a predictable nonce, you don't get the protection that you want. You can look at the OpenSSL wiki for some guidance as to how to implement this properly, and you find lots of great warning statements. These are like the warning labels that Laurie showed earlier. So you have to set up a 256-bit key and a 128-bit IV. Make sure you use the right key and IV length for your cipher, or it will go horribly wrong. I'm not sure exactly what happens in that case, but I guess things can go wrong. And you have to set up a buffer for the ciphertext, and you need to ensure that the buffer is sufficiently large, or you may see a program crash, or it potentially introduce a security vulnerability. And it doesn't tell you, by the way, how to ensure that it's sufficiently large. You have to somehow figure that out for yourself. And this is the kind of advice that you'll see, the kind of documentation that you'll see. And maybe there's better out there, I don't know, but well, I guess there must be. But this is what I found on the official OpenSSL site. And so you can see from this, I think, that developers need help, right? And it's sort of not their fault. I mean, I can't really blame them for the fact that they're introduced to this level of complexity and then getting it wrong. And in fact, there's a recent paper at Oakland, co-authored by Michelle Mazurek, who's a colleague of mine at the University of Maryland, looking actually at how developers deal with this problem. And among other things, I mean, I'd encourage you to go read the paper, but among other things, showing that app developers very often turn to Stack Overflow for programming help. Actually, Michelle's in the audience, so she can correct me if I get anything wrong, or you can ask her afterward. And how valuable and dangerous is that? Well, it turns out that actually only 17% of Stack Overflow posts had secure code. And I think in this case, if I remember correctly, they were not looking specifically at crypto. They were looking at general secure code, but I'm sure it holds for crypto as well. And then they were actually analyzing, how much better developers could do with or without access to Stack Overflow. But the point I want to make here is only the fact that we see that developers are having difficulty writing secure code. They're looking for places to find good advice. They're apparently having trouble finding it from reputable sources. Well, I don't want to say that Stack Overflow is not reputable, but I mean, you would think that there would be some canonical reference that they could use rather than relying on random posts from random people that have no real provenance. And again, the fundamental problem here, I think, is that, from my point of view, I think this is really true. Why should a developer need to know anything about any low-level crypto details, right? It would be much better to be provided with an interface to encrypt, right? So if you go back to my slide earlier that had this complicated structure of how to construct public key encryption, as a developer, one shouldn't care about any of that. The only thing they should care about is having this interface that allows them to provide, say, either a message or a key and a message even, and be able to encrypt, and another interface, say, for doing authentication, if you want to do message authentication, and maybe one that does both automatically. And in fact, we're seeing now some newer crypto libraries, some more recent crypto libraries other than OpenSSL, actually work in this way. And the NACL library that I'm most familiar with does exactly provide this interface, this high-level interface to an encryption box, as it were, and allowing programmers to use it without having to understand any of the underlying low-level details. And along with that, I think the API documentation needs to improve. In the OpenSSL roadmap, actually, they had it listed as an open direction. Something that they were actively trying to improve is exactly to improve the documentation. That's been there since mid-2015. I don't know if any progress has been made. I looked last night. It's still there now in the 2016 version. I guess they're still working on it. So let me turn to the second part of my talk, which is about misunderstanding cryptography on the part of developers, I suppose. And to set the stage for this, what I want to just talk about very briefly are what I see as the core principles of modern cryptography. And this is what I teach basically anytime I cover cryptography in a class. And I can go on for 45 minutes just about this. But for this purpose, I just want to focus on these three principles and how developers should be approaching these principles. So what I see as the three principles of modern cryptography are formal definitions, clearly stated assumptions, and then the possibility of proofs of security. And the latter one in particular allows us to move away from this design, break, and patch cycle and get things implemented, get things deployed that we have some actual mathematical confidence in that they actually are secure. And the most important one for developers, from my point of view, is the formal definitions. So formal definitions, right, you can think of from the point of view of a developer as, number one, defining the syntax of the API. OK, so we know that encryption takes a message and a key and outputs a ciphertext. But also, it allows for an understanding of the security guarantees provided by that API. Just again, as an example, to reiterate something I sort of said in different words before, if you're using an API for something that tells you it's a semantically secure encryption scheme, then it assures you that a passive adversary learns nothing about the message from the ciphertext. Right? That kind of a statement is what's important from the point of view of a developer. Now, of course, if you're a cryptographer, if you're taking a dedicated cryptography course, you can mathematically and rigorously formalize that. But even just some sort of a high-level understanding of that kind of a definition is important for the developer to have. And that is basically all that should be exposed by what I would say is a proper crypto library, right? This API of the syntax and what security guarantees that object provides. And I can't really hit home enough how important I think these formal definitions are. And actually, I think that from my point of view, of the three principles I listed earlier, I think the formal definitions are the ones that are perhaps most important and most central to cryptography. Cryptography is actually the only field I know of where definitions are taken as a first-class object, by which I mean that people actually write papers about definitions, comparing definitions. Is this a good definition? Is this a bad definition? Does one thing imply another definition? And things like that. And I know definitions are used in, of course, lots of other fields, but I think crypto is the only field I know of where people put as much care and study on the definitions themselves. And more generally, right, specifying a threat model is critical. So this should be both for the system at large, right? You want to specify what threats are in scope and what are out of scope and what you're trying to achieve by your system. And then, of course, for the cryptographic components within that system, right? I'm using encryption here. What am I assuming that this encryption box is providing in the context of my system? Assumptions are also important for modern cryptography because most of modern cryptography relies on these unproven assumptions about what are hard mathematical problems. And so we have to just get over that. But I think, again, from the point of view of a developer, the important thing to be aware of is just to be vaguely aware when an assumption is close to being falsified, right? So when MD5 should be deprecated, when RSA 1024 is considered too weak. But even there, I don't think it's actually the job, ultimately, of the developer to have to be aware of all this. It would be much better if this were handled automatically by a proper crypto library, right? So when MD5 is deprecated, the crypto library should provide an update that swaps out MD5 for SHA-256. Proofs are, of course, also important for what I do as a cryptographer. But again, from the point of view of a developer, the main takeaway here is just the very fact that crypto schemes can be proven secure, always relative to some definition and based on some assumption. So you have to interpret any security claim with those two things in mind. But the other thing to understand is that these proofs are brittle, right? And they're people, if you look at a crypto proof, you can see that there's a lot of cases to take into account and a lot of different things to consider. But what that means actually is that if you change anything in the scheme, then you risk invalidating the proof. And if you've invalidated the proof, then in the best case, you have no more provable guarantees about your system. And in the worst case, you've exposed yourself to a crypto flaw. And going along with this is, of course, the maxim of not designing your own crypto. Which I guess I kind of took as a given, and I didn't have it up there on the laundry list originally. But the fact that these proofs are so complicated and that anything you design, unless you're going to give it a proof yourself, is not likely to be provably secure, you should question why you need to design any crypto of your own. Now, what about constructions? What about all the cryptographic schemes that we like to teach people and CBC and all these fun things? Well, actually, I would claim no. I would claim these are of really secondary importance for your average developer, for your average user of crypto. And I think this is actually a problem. I think this is actually a fault of the way crypto is taught. And I would suggest that when we teach crypto to a general audience, right, in the context of, say, a security class, it would be much better to focus on definitions and secure usage rather than trying to present details of schemes that are probably going to be incorrect. Right? So when, I don't do this in my class, but when I see a lot of other people teaching computer security, they teach, hey, this is public key encryption, this is what it can do. Here's an algorithm for public key encryption, textbook RSA. I mean, why? What's the point of that? Because it's an insecure scheme. But I would claim even beyond that, even teaching a secure scheme, it's just irrelevant to somebody who just wants to use the crypto. And I think this approach can hopefully lead us to a situation where these common flaws will be more readily avoided. And I wanted to maybe walk through two examples in the time I had left. These are, again, two common examples of crypto flaws that come up, and maybe pointing out why I think those flaws occurred. So if you look at some descriptions of encryption, right, you won't see a clean definition of security of the kind I had up earlier, namely that the ciphertext leaks nothing about the message. Instead, you may see claims like, CBC mode encryption produces random-looking ciphertext, and we can view encryption as a black box that scrambles the message. And what someone might conclude from this, and it's not just a might, it's actually people have concluded from these descriptions, is that encryption by itself should also provide message integrity, right? So if my encoding algorithm, if you remember back to that animation slide I had, looking at message integrity, so if I just take encryption as my encoding algorithm, it's very natural to think that because the encryption algorithm is producing random-looking stuff, how could an attacker possibly generate random-looking stuff that's going to possibly decrypt to anything valid? But this, in fact, has led to, for example, many authentication protocols built and broken based on this incorrect reasoning. So the idea here is that you build if you believe encryption provides integrity, then you can authenticate somebody in a challenge-response protocol where the challenger, the verifier, will send a random nonce, and then the other side will compute an encryption of that nonce and send it back. And then the challenger will decrypt and check whether they get back the original challenge that they sent, right? And the problem is that that doesn't work. Encryption in general does not provide integrity. Now, how could this have gone, right, if in another world, right, in a world where maybe we're teaching crypto to the masses properly? Well, the first thing the developer would do is think about what is the desired security, what's the threat model. And in this challenge scenario, the threat model is roughly that if you have an impersonator, somebody who's not actually the true verifier, they should be unable to respond correctly to this random challenge being sent by the verifier. Or a little bit more formally, they should be unable to properly encode a random challenge sent to them from the verifier that they haven't seen before. And you think about it a little bit and you say, well, if I plug in encryption here, is there anything in the security API of semantically secure encryption that would imply anything about this property? Well, no, because nothing in the definition of semantic security says anything about whether I can encode a random challenge or not. But you think about it for 5 more minutes, and then you realize, well, the appropriate primitive here is actually a primitive that provides message integrity, i.e. a message authentication code. And if you plug in a message authentication code to this challenge response protocol rather than an encryption scheme, it actually will be a secure authentication protocol. Another example is you look at hash functions and you see all kinds of comments about hash functions producing completely random looking output, where changing even 1 bit of input results in completely unpredictable output. Well, if you believe that, then it must be OK for me to construct a message authentication code by just hashing the key and the message. Because if the attacker doesn't have the key, how are they going to possibly be able to come up with the output of the hash and the key and the message for a message of their choice? It's simply not going to be possible because this hash is just outputting random stuff. And again, many integrity mechanisms have been built and broken based on this incorrect reasoning because it admits what's called a length extension attack that I'm not going to go into. But thinking more generally about how this could have gone in a different world, well, again, what people could have thought about is what's the desired security in this case? What's my threat model? And the threat model is exactly message integrity. Well, if I plug in a hash function that's guaranteed, say, only to be collision resistant, does a collision resistant hash function say anything about whether I get message integrity from hashing the key and the message? Well, there's a definition mismatch. Nothing in the definition says anything about it, so I have no idea. But in fact, again, you think about it for 2 more minutes and you realize, well, if I want message integrity, why don't I just use a message authentication code that people have already studied and proven secure? And then you can plug that in instead, and of course that will give you the message integrity that you want. So just to summarize what I've said here, so many crypto flaws that we see in practice seem to me to result from the same underlying cause. Namely, a developer's exposure to too much information about the low-level implementations rather than abstract specifications. Think again about cryptographic schemes versus clean, easy, and clear crypto APIs, and cryptographic constructions versus cryptographic definitions of security of what the construction, or what the primitive, I should say, provides. And I think from that point of view, there's a lot of work to be done still on doing a better job on the part of the crypto community in developing better crypto libraries. Developing these crypto libraries that only expose an API for the desired high-level tasks and don't expose the programmer to the messy details that are really irrelevant for what it is they're trying to accomplish. And at the same time, I would claim that developers should focus on the security goals rather than on the low-level details about schemes. And I'll go back and reiterate what I said earlier, that I do think, I'm not claiming that nobody should learn cryptography. Cryptography is great. Cryptography is fun. I teach a cryptography course on Coursera, and it's fantastic. But that's secondary. I think you can learn cryptography, you can learn the low-level details after you understand the high-level security goals that cryptography provides. And at the same time, I would claim that if you don't want to learn the low-level crypto details, you shouldn't have to in order to get crypto right for your application. So I wanted to leave a little time for questions at the end. I guess we have a couple of minutes. I don't know how much we're going to go into the break. But I'm happy to take any questions if you have any.
And as before, if you could help us out by walking up to the microphone, that would be great. And we can ask questions from there. So while people are coming up, let me just... Yep.
Hi there. I have a question about if you're implementing something that needs to talk to something else that already exists. My experience with these high-level libraries is that it provided a very fixed, nice interface, but if I need to talk AES 256 and CBC mode to something else that already knows how to talk about that, or I need to develop a certificate bundle that browsers around the world will process, How do we avoid getting into these low-level details because you're trying to fit what you need to do into something that already exists? Maybe this is a bootstrapping problem.
So, I mean, there's some fundamental limitation, right? So if I have already implemented on some device somewhere else my own crypto scheme that I've hand-rolled, then it's not likely to exist in any crypto library, and I'm going to have to build the matching side myself, right? The idea would be to avoid that possibility. But even if you're using a standardized scheme like CBC, CBC mode encryption, let's say, right? So even there, what I would say is that it would be much better to provide the developer with an interface for CBC mode encryption rather than for the CBC mode function where they have to remember to choose the random IV and to do things properly. So even there, I mean, you do have to find the right balance. And I was actually talking with somebody this morning over breakfast about this, that in some cases, right, all you want is a box that encrypts. In some cases, what you want is actually something even higher level. You want something that's going to provide a secure session that also protects against replay attacks. And those are two different levels of abstraction, and you have to pick the right level. And it will be a challenge, I guess, to either have libraries that provide things at all those different levels, and then you can choose the level you want to work at, or just have different libraries available, each suited for different purposes.
Can you talk about some of the impediments for why there's not libraries like you describe, or if there is work headed in that direction, pointers to that?
Well, that's a good question. I mean, I would guess some of it is probably legacy, right? So people have things written using an OpenSSL library, and it would be a big pain to update that. But I don't have really the best answer for that. Probably some of it is just what's the word? Knowledge, right? So if you're a developer and you're sitting down from scratch to write some program, you've probably heard of OpenSSL. You probably haven't heard of NACL. So really, part of it is just getting the word out. But actually, people in this audience would be much better suited to answer that than I would be.
Okay, so you talked about NACL being nice in that it provides higher level than just low level crypto stuff. Have there been any user studies showing that it's actually useful?
So that is great. Actually, this is something, and I saw this bullet point in Laurie's talk, right? She said that cryptographers don't run usability studies. And I didn't know actually what would be worse, the fact that I don't run usability studies or what would happen if I did. But basically, so no, I don't think so. I think what would be great actually is a study like that. Well, yeah, so I think a study like that would be great. I think another thing that would be great, but is much harder to do, would be to look at different approaches of teaching crypto, right? So follow a crypto approach where you teach all the low-level details, follow a crypto approach where you just teach the high-level things, and then see which class of students does better on just implementing a secure chat application after the class. But I think, like I said, there are some there's only two works that I know of. The one that I mentioned that appeared in Oakland that was looking at developers' use of Stack Overflow. And there's a related talk that tutor Dimitris is going to give later today, but I don't think you studied users. Is that right?
Actually, I think that's what Michelle does. She looks at these.
OK, so maybe if Michelle's here, she can comment. But I think, anyway, the point is it's in its infancy, and I think more of those are needed. Yeah.
One last talk, last question rather, yeah? If we could load up the intro picture.
Letting alone the fact that Salt library, while it has very nice concepts, what you call NACL, does not work on all the platforms, partially because of how it is designed to be built. How do you see using interfaces like that, which say deprecated MD5 and now use SHA-256? If you happen to need to, say, decrypt and authenticate a file that has been archived 2 or 3 years ago.
Yes, this is related, I guess, to the first question about backward compatibility and compatibility with existing devices. And I actually hadn't thought about that specific question. And it's an interesting question philosophically, I think, right? Because ultimately what you're saying is that we have these things archived that are being integrity protected, but the integrity protection is meaningless. So maybe I would argue, I mean, OK, it's not going to be better to throw it away because at least maybe it provides you some barrier. But it's a little bit of a in some sense, a strange question because of that. But yeah, in that case, you're going to have to use the same crypto library that you used to implement the original.
OK, let's thank our speaker. And as before, we have a small token of our appreciation. Thank you very, very much.